Welcome everyone to this workshop on quantum and AI. I am Xavier Aubry. I'm the founder of Vinci Labs, one of the partners in the UAC project. And today we have a very exciting panel of speakers who will be presenting different aspects of the quantum and AI revolutions. This should take us to around 4 p.m. today. And we'll have time for some questions, of course, after each session. So to present you a little bit about the challenges that we have in front of us and the exciting revolutions that come around, the first one is the quantum revolution. It actually has already happened. The first quantum revolution, as it's called, was really at the beginning of the 20th century, with researchers starting to understand the flows of particles and the effect of those flows. For example, flows of electrons in order to create a transistor and then a microprocessor, or flow of photons that led to the invention of lasers. So very exciting things that have really shaped the way we interact with technology now, because what we have in our pockets, our phones or laptops, they are all coming from this first quantum revolution. In the meantime, another revolution took place starting in the 50s when AI was coined at the Dartmouth workshop. There was not a lot of progress between in the 70s until the 70s, and then of course large progress started to happen around 2010 with the rise of GPUs, open source frameworks, big data. That led to the first wave of AI innovation, particular machine learning. And now in 2020 to 2025, we've seen the emergence of the large language models, LLMs, which has enabled a completely new category of generative AI applications. This is the tip of the iceberg. Of course, machine AI is much more than just generative AI. There's many other domains like machine learnings. But what we see across the AI landscape is that in general, the technical performance of AI has now caught up or even surpassed in some instances with human performance. So we have algorithms that are able to generate results which are on par or superior to human capabilities in many domains. But there's some exciting stuff coming, and that's the second quantum revolution, which has started in this century. And it's about controlling individual particles. We saw the discovery of quantum phenomena, superposition, entanglement, and we start to understand how to exploit these quantum properties at the level of an individual particle. And that leads to these new fields of research around computing, with a range of modalities used to produce the first quantum computers. You've probably heard of superconducting qubits, ion traps, neutral atoms. These are different types of quantum technologies that can be used to create a quantum computer. And we have the first prototypes, small-scale quantum computers already available today. But quantum can be used also for communications, in particular to secure communications, as well as for sensing. There are already quantum sensors available capable of doing some very precise measurements, for example, gravimeters, which are using quantum mechanics. So this is what we have today in front of us. There is a lot of applications, industry applications, typically problems that can be solved with quantum technology are around different types. Simulation, optimization, machine learning, cryptography are some of them. And in each of these domains, there are massive industries that could benefit from these applications. But we are at the very beginning. The computers we have are still very small. They use a small number of qubits, which are very noisy, and therefore they are prone to errors. So we can't really yet solve problems with quantum computers that cannot be solved with classical machines, but it will come, and it will come fast. Most producers of quantum computers estimate that this barrier will be reached in the next 5 years. So this is really around the corner. And that's why, as a company, it's essential to look at the quantum revolution together with the AI revolution, because these will go together, and see what can be done with it, what kind of partnerships should be done, what kind of technology should be tested. So this is the goal of today, to explore this a little bit further. Now, I would like to pass it on to our second speaker, who is coming from University of Pisa. Vincenzo Lomonaco is an assistant professor. He's also a project member of the project Emerge, a project funded by the European Commission around AI. He is the CEO and co-founder of Continual ST, which is a spin-off of University of Pisa, and serves as the founding board member of Continual AI, which is a non-profit research organization and a open community on continual learning for AI. At University of Pisa, he works with the Pervasive AI Lab as a task leader in 2 major European projects, one of them being Emerge. And he's an investigator in multiple industrial research contracts with large companies like Meta, Intel, Leonardo, and CVision. He's also among the 350 Italian researchers selected for Future Artificial Intelligence Research, so-called FAIR, which is the largest Italian initiative on AI with a budget over 110 million. He's also a proud member of Project Alice and Claire. In 6 years of research following his PhD, Vincenzo has secured over 1.7 million in R&D grants as PI, including the Fondo Italiano per la Scienza, FIS in Italy, starting grant. In 2023, he's obtained his National Scientific Habilitation for Associate Professorship and has authored more than 80 papers published in conferences and journals. Vincenzo, the floor is yours.
Thank you so much for the introduction of Vincenzo. It would be a delight to have him as a speaker, but it looks like he has not been able to join, and he has not been responding to my emails over the past few minutes. So hopefully he will join us as the next speaker. But in the meantime, if we could please hear from Hendrik, who has kindly volunteered to step in, and we will basically switch the speakers. Hendrik will go first, and then Vincenzo, if he joins us, he will go second.
That's good. I will introduce Hendrik. Hendrik is a colleague working at Capgemini Engineering as an engagement manager. He's been involved in a project also funded by the European Commission called Equality. This is a project about developing quantum algorithms on existing small-scale quantum computers. As part of the National Centre of Excellence for Research and Innovation at Capgemini, he's driving research activities towards industrial implementation, a very important aspect of this. This is someone who is used to take technology out of the lab and bring it to corporate partners and companies in general. Before joining Capgemini, Hendrik earned his PhD in physics through a joint program between University of Mainz and the Tohoku University, I assume, in Japan. Thanks, Hendrik, and the floor is yours.
All right. Thank you very much, Shahid, for the introduction. I hope you can see my screen now. And I would like to start here my presentation to bring you a bit closer to the topic of quantum and how far are we already, what kind of projects are we already doing with our industrial partners, what are we doing in the Equality project, and to introduce you a little bit to this topic. First, want to introduce you to how are we here unleashing the potential of research and innovation here at Capgemini. How do we help accelerate here technologies like quantum from the academic level and bring them towards industrial applications. And just to briefly recap, to briefly present to you, so we at Capgemini Engineering are of course part of the global big Capgemini group. But here at engineering, we also have around 50,000 engineers, physicists, mathematicians, scientists, chemists that are focusing really on engineering challenges. And this is across a whole domain of different industries where we take our global footprint, our global solutions, and apply them here to specific problems to create solutions for our partners, for our clients, and together with partners from all around the world. And here, where I'm situated here in research and innovation, what we are focusing on really is when we look at the technology readiness of a new technology that you develop, that you have an idea for in your brain, in your lab, to elevate this level of your technology. And you often, in this kind of funding schemes, you talk about technology readiness level. And here, what we are focusing on is if you have an idea, a concept for it, if you have an experimental proof of your idea, we help you to elevate this solution towards an industrial prototype, basically demonstrating, hey, this really works in the industry. And then to really implement it, then also on industrial scale, this is something we as a company can also help with, but the projects that I'm involved in are here on this fundamental scale, helping you to accelerate here your technologies, your ideas, your innovations. And as I already said, we focus here on a variety of different key domains and areas. And this ranges here from mobility topics to healthcare to also sustainable topics. But also, especially in the energy sector, we're looking also at hydrogen, fuel cells or battery development. How can we accelerate this? How can we bring ideas from the lab, from academia, together with industrial partners into the industry? And just to give you maybe a very, very big overview, I know it's going to be like a bunch of projects, but just to show you like a few of the logos, a few of the projects that we have been involved in here on both German funded projects, but also on a European scale. What have we all been involved in? There's a variety of projects ranging here from the mobility topics, where we, for example, do traffic management projects with AI, analysis of the traffic, up to also the quantum projects like equality that I'm going to present to you closer today, and also new projects in the quantum sector like Almanac QC, where we look at digital twins of a quantum computer, or also the topic of post-quantum cryptography, as we already mentioned, an upcoming very important topic also to keep our devices secure. Now, I cannot go into detail here. I hope you recognize here one of those logos. What I want to take you from this is that it doesn't matter in which industry you're located in, with their connections, and we have also experience in driving innovations in these different types of industries. And we also have the partners there. So in all of these European projects, we have partners from academia and from industry that we work with together. And just to give you a brief overview, these are just like an excerpt from all the industrial partners that we're working together with on these type of projects, ranging up to very big players like Airbus, Infineon, also Porsche. As you can see, like covering like the whole scale of industrial partners that you can think of, and also combining it, of course, with the academic excellence that you can find at universities, at research institutions, and also across Europe. And that is our key goal, to connect industry and academia to really drive their innovations, ideas, and also to make sure that we achieve here industrial impact at the end. Because this is important when you kind of develop these kind of new ideas, that you always have to remember what is in the end like the use case in industry, what is the industrial problem that we would like to solve here. And I hope with this, I've given you a brief overview about what we do. Now I would like to dive a bit deeper into the quantum topic and also into our equality project, where we do exactly this. We take our industrial partners, our academic partners, and we look how we can use the quantum computers that we already have available in the most efficient way. And at the end, I'm also going to look a bit further into what type of projects are we already tackling apart from that, like with our industrial partners, with our clients, what other fields are we already actively employing, where does industry see here really short-term value that can be gained by quantum computers. So this is what I want to do with you today. Now, quantum technology, we've already had there this very nice overview. You can generally separate it into these kind of 3 domains. When you talk about quantum, you can talk about quantum computing. So quantum computers that are an evolution or a new way of computing, basically. What is important there to remember is a quantum computer is nothing that will replace the current computer you're using to look at me or that you're using on your phone. It will not in general replace every device that we have, but it will be used for key applications to solve key problems that we face in industry and in general in the world. And this can range from topics from material science or drug discovery, also to more advanced topics like risk modeling in the financial industry or other areas. Then there's a second field, and this is quantum communications. Now, one idea here is that you can use, for example, also the properties, the quantum mechanical properties of a photon or of other quantum elements to basically secure your data, make it quantum secure, that you have that use quantum key distribution to secure your data and to prevent any attacker from decrypting it. Another area that is already now relevant is post-quantum cryptography, because you might have data right now that you want to protect also in the future from attacks by quantum computers. Their big risk is that already now I can steal your data on how did you do your drug development, how have been your financials for the past 10 years. I can take this data, I can store it, and in 5 years or in 10 years, whenever the quantum computers are ready to crack the current encryption, one can decode your data. And there it's important to already now start to migrate, start to change to new ways of ensuring and encrypting your data. And then there's the third field, the quantum sensing field, which we already mentioned that there have been a lot of recent advancements on how can we use quantum properties on the atomic scale to use them to measure, for example, the magnetic moments when you have an Vinci Centre microscopy to measure very accurately small changes in the magnetic field, or also small changes in the gravity of the Earth due to what lies beneath the ground, basically. So these are all very exciting domains that are currently explored, funded, and there's been a huge push over the past years in the quantum field to really get the most out of this and to take part in this quantum revolution. Now, I said already quantum computing can be used here to accelerate our process in different areas of problems. And what you usually consider here is that we already have problems that we can't solve, but maybe quantum computer can solve them easier or faster or more accurately. So there are problems, for example, in optimization problem, where you can think maybe of a pizza man like in New York going from house to house delivering the pizza, and he needs to plan the smartest route. It's simple if you just consider one pizza man and one constraint, like the route or the distance that he needs to travel. However, the more complex a problem gets, the more harder this gets to solve when you don't anymore look at just New York, but at the whole world, and you deliver billions of pizzas. The whole problem can get really hard. And the more you can try, the more objectives you introduce into such optimization problems, the harder they get to solve. So even though we can solve those problems, quantum computers have the capability and the possibility to drastically reduce the effort that we need to put into solving these problems. And this is a huge advantage here. So in this case, quantum computers could help us to accelerate a problem, to accelerate the solution for the problem. Now, one other area where quantum computers also pose a risk, I already said that they could decrypt in the future current encryption methods, but another potential area where they have a huge potential is when you use a quantum computer to simulate a quantum system. And this is maybe the beauty of quantum, where nowadays when you have a chemical problem like for drugs, drug discovery, or for material science, then you need to emulate quantum mechanics. However, if we have a quantum computer, we can directly use quantum system to simulate the quantum system. Thus, we can get more accurate results. So this is a big advantage of quantum computers. They can either help us here to solve a problem that classically is quite hard, much faster, reducing computational power, reducing the time that we need to solve the problem, or they can allow us here to solve a problem more precisely. It's, for example, here in the camera use cases. Sometimes they also do both, but let's just take this away that this is what quantum computers can do. They can help us here access problems and to solve problems on a shorter time scale than we might have thought before, or with a much greater accuracy. Now, this can happen across a variety of application sectors. This is just one example, one graphic to illustrate, to give you a bit of an imagination of where quantum can all be useful and where it all has an impact. For example, here in finance, you could also use advanced optimization routines to look to find better minima or better ways to optimize your portfolio, or in the chemical industry. Of course, you can use it here to find new materials, not only for batteries, but also for fuel cells. What I would like to do here is to give you an example of how is this done, like who's looking at these problems. And the answer is we are already looking there, together with also other partners from industry and academia inside our equality project. We are already looking here at the subsection of these problems. And with this, I would briefly like to introduce to you equality, where we have here the aim to look at efficient quantum algorithms for industry. And the basic idea or the basic concept here is that what do we want to do in equality? We want to use the quantum hardware that we already have today available, and also in the next 5 years available, in the most effective way. So we already want to now develop cutting-edge quantum computer algorithms that can solve certain strategic industrial problems that we deem very relevant. And these topics are, these use cases are distributed here across a variety of domains. So looking here at use cases from aerodynamics and aerospace, also at optimization use case and space mission optimization, and also at these chemical use cases in energy storage materials and systems. So all of these areas have one thing in common. They are very complex. So solving these requires either a trade-off between how precise or accurate you want the solution to be, or very long computational time that is needed to solve such a problem. And here we are certain that quantum computers can provide here a competitive edge in the future to the ones who solve these problems first. Now, who are we partnering up here with? Here you can see this is the whole consortium. We have here partners from all across Europe with the Vinci Labs, Airbus, Fraunhofer Pascal, Unileiden, DLR, and INRIA, from France, Germany, Netherlands, just bringing here excellent partners together in order to create these real, these quantum algorithms for real problems. And with Pascal, we also even have a real quantum hardware provider there, allowing us really to cover the full software stack to make sure that the algorithms, the solution that we develop, can also, in the end, be practically implemented on hardware. And what is the approach here? So I said already, Pascal is one of our partners, and Pascal is a quantum hardware provider. But of course, there are also other quantum hardware providers. There are also there are different types of quantum computers in general. The most famous ones that you probably have heard are the superconducting ones. But there are also different hardwares like red-ion hardware, neutral atom hardware. And what we want to make sure here in this consortium is, of course, that we do not try to focus too much on just one single hardware. We still want to make sure that the type of algorithms, the type of software, the stack that we develop is hardware agnostic, so that you can run on potential different hardware types, that the solution that we develop here to better utilize the noisy qubits that we have currently are not just for one single system, but can be implemented across a variety of different hardware platforms. The same here also for the use cases and the algorithms that we develop for them. We're now looking here at different industrial problems, as I said already, from aerodynamics, energy storage materials, and space mission optimization. However, like the algorithms that you need to develop to solve these problems, these are very basic algorithms sometimes that can be transferred easily to other types of hardware or software. So differential and stochastic differential equation solvers, for example, are needed here to look at the aerodynamics use case, but are also relevant here for other use cases and for other problems in general. I think everyone who has solved a differential equation in school knows that are quite important, not just for one single use case, but all around the world in solving physics and solving problems. So what I would like to do here now is to inspire you a bit by looking deeper here into the use cases. What are we looking at here? What type of problems can we solve with quantum computers? So the first one I would like to look at are here the energy storage materials. So you know that we are in dire need of new energy storage technologies in order to fulfill the need here for a green transition in our society, to tackle climate change. And what is really nice is that quantum computers can finally help us here to look for new materials, to better understand the systems that we already have. Because when you do these type of chemical simulations, you always have to make this trade-off of how accurate in your TFT simulation or calculation, for example, how accurate do you want your result to be, and how many atoms would you, for example, actually include there? You cannot include all the atoms of the material. You can often only include like a very small subpart in order to still get a result on time calculated there. So this is like one of the issues here where quantum computers can help to overcome here this trade-off between precision and scale by allowing you to tackle larger systems with a higher precision. And a key element or a key thought that you need to understand here is that quantum computers are excellent here at tackling problems on the electronic scale, like on the very narrow, on the small scale. And now what you always need to keep in mind is that this is a key information that you need to transfer from the nanometer scale to the millimeter scale, to have a multi-scale approach here in your discovery, from the very small electronic structure of an atom towards how atoms interact with each other, to what influence does this have overall on the battery properties in the end. This is something, or an approach that we look at here. Another area that we are looking at is also aerodynamic simulation and optimization. This is a use case that Airbus is, of course, really interested in, because you can imagine that when you have here an airplane and you simulate here, how does the wind go here around the wing of my airplane? This simulation is very compute intensive and can take a lot of time also. You can see here in the background, like all these type of like small meshes here. And the more accurate your meshes, the more time it will take in the end to calculate here. Yeah, how does the air flow around here, the airplane. And here the idea is that while the simulations nowadays can take like a week, for example, quantum computers could accelerate these problems, allowing you to faster solve this problem, thus decreasing the time that you need to cycle here through different design elements and allowing you to more easily find the optimal aerodynamic solution for your problem. So here we try to tackle computational fluid dynamic problems with quantum computer and developing here the fundamental algorithms to solve these type of issues. Now, this was one of the examples from aerospace, but we also have here a second one, which focuses more on optimization. This use case, space mission optimization. What is the basic idea? The basic idea is you have a satellite, and this satellite is moving over the Earth. You can see it here, like this white line is moving over the Earth, and it has the target to acquire pictures of different points on the Earth. Now, because it has to do that, the satellite needs to rotate, needs to optimize its position during a certain time window, because it's moving in space. The time it has to do or to conduct this operation is also limited. So if a time-limited optimization problem you need to fastly solve, depending on a variety of different parameters, your equations and your solution to find the optimal path, the optimal routing and angle of the satellite. And that this optimization problem, that is something we're tackling here. Inequality also helping us here to better understand how can we use quantum computers to solve such optimization problems. And this is also a topic where we can then transfer this knowledge afterwards also to different use cases, to different problems. Because only because you have one problem and you create a solution for one problem, you also have often the possibility to use your solution for a different type of problem or in a different type of industry, and to use the same expertise that you've developed there and to apply it there. Now, the next use case that I've brought here from equality is space data analysis. Now, in space data analysis, what you do is you have a synthetic aperture radar. You basically send an electromagnetic wave from space, from the satellite towards the Earth. You collect the reflective electromagnetic signal, and then you need to do some type of calculation to calculate back, okay, what has changed in this electromagnetic wave. And there you don't just use from one satellite or one point in time the image, but from multiple points in time or from multiple satellites. And then you need to process this data, because initially it looks like this. Here on the left side, you can see it's very noisy, it's very rough, and you cannot really make out anything. But by processing this data, which can take a lot of time, currently with the HPC systems, you can get here this nice image of the Earth, of the Earth's surface, and you can make out like different roads, different airports. You can basically analyze now the data. But here, in this type of use case, what we are looking at is how can we use now quantum machine learning techniques to accelerate this data analysis? How can we use the quantum computer to accelerate here the way we analyze this data? Now, this hopefully has given you just a very brief, very good overview over the different use cases we tackle here inside our quantum project. So if you would like to know more about the different use cases, but how we're actually implementing those solutions, please check out our website. You can find the papers and publications. You can just have a deeper look into these type of problems. However, now I will just briefly put this into context. I'll also explain a little bit how does this fit into our broader vision of where is quantum computing today, and also where is it going. So far, I've talked here about these research projects, but this is not an isolated effort. We're not just part here of the quality project. We have a whole quantum lab here at Capgemini, where we collect the experts from all across the globe, like all the scientists, all the experts, and where we collaborate inside the group, but also with partners from different industries in order to create here quantum solutions for our clients, for our partners. And these partnerships, like with IBM or Pascal, are really crucial, enabling us to really develop your quantum solutions together with you, and that can really tackle your kind of problems, your kind of use cases. And this is a key aspect of this emerging field of quantum computing, that you need to work together in order to get the best solutions. And this is something that is really like key here, and also a really nice environment. Now, maybe where do we see here a big benefit to be gained? Now, in the near term, where we see here a big benefit to be gained is by using hierarchical models, where information from the quantum computing system, from the quantum computer, from the small quantum machines that we already have, can feed into other systems. So basically where we can combine quantum simulations with classical simulations and bring this together also with machine learning in a kind of hybrid approach, a hybrid model that allows us here to tackle the whole range of a problem, from the molecular level, where you have your different electronic structures, to the macromolecular level, the systems level, and in the end, the continuum level, where you have your mechanical properties of a certain machine or a certain problem. And this is something that we really think here is not something new, but that also like extends what we've been already doing, and we're happy there that we can partner up here with different partners, different institutes to achieve this, where we can really then provide here and help to use the input that you have from the current quantum systems, or that you can use this in your other modeling approaches, in your simulations, to create more accurate, better results for you. And you might now ask, is this really important here to use a quantum computer? It is. It is essential for a bunch of problems that we use here a quantum computer to get more accurate results on the atomic and molecular level. Because if you use these type of machines, you can get very good information, very exact information on the atomistic scale. And this is always used as input for other modeling perspectives. And maybe you know the saying, like if you put something bad into your algorithm, you will get something bad out. And that's the same here. Basically, the more accurate the input you have for your other approaches, the better your end result will be. And this is where quantum accelerates. And this is also where we see there huge possibilities coming here in the chemical sector, where you can combine and high performance computing, quantum computing in a hybrid approach to just like take a small task, like this small subtask of your problem, put that onto the quantum computer, and then do the further calculation again on the high performance computing system, basically bringing together the advantages of both systems in the way that we currently have, and to make sure that we already can use the quantum computers that we have today. And here, now last, I just want to give you like a brief overview here over the type of different products that we have been looking at with our partners here in industry. You can see we've talked about the equality project, but it basically has here a wide range of topics that we're tackling. Here we're looking at drug discovery problems where we can use quantum computing to have more accurate understanding of how our drugs are acting with each other, battery chemistry problems, but also problems that maybe you didn't think about can be better solved with quantum computing, like corrosion. It's not a solved issue, but there are a bunch of problems in the world that we can have a better understanding with quantum computing. And I think with that, I would like to conclude and to leave you with a message that I'm sure you also have a problem that can be better solved with quantum computing. And if you think we can help, reach out. Thanks a lot for your attention.
Thank you, Henrik. Very interesting presentation. I think we have a number of questions. We have a bit of time to address a few of them. I think the first two are more for you, Hendrik, a bit more technical, focusing on Capgemini, and there are a few questions which are more on the market space, which I can also help to answer. So first question, Hendrik, is focusing on real-life application. You went through a number of them in this presentation. You mentioned the traveling salesman problem. Are these, do we have real-life problems that can be solved with quantum computers right now or not?
So we have the problems that can be solved. I don't think we have the computers right now in this moment to solve them. So there are a bunch of problems and people looking at them. So from my understanding, the point where we have a real quantum advantage, I mean, that's a current topic in the industry in general. Like when do we have this? When can we officially pronounce that this is achieved? So I think there's a lot of hype. There are some more mathematical problems that have been solved, or it has been shown that they can be solved faster with a quantum computing system that is already out there. However, I think the real industrial application, we are not at this moment there, but it will become soon reality. That would be my view there.
Thanks, Henrik. I have to agree, complement the answer. I think typically what vendors are saying right now, the quantum computing companies, is that you need around 200 logical qubits, a logical qubit meaning an error-corrected qubit, which probably will require around 10,000 physical qubits, assuming we have good error correction systems. But 10,000 qubits is just not yet there. The biggest computers have around about 150. If you look at superconducting, maybe we'll see 1,000 qubits in neutral atoms. So as a result, as Henrik said, we have some small computers. They cannot solve the big problems yet, but they should be able to. Right now, what we can do is we can emulate those behaviors on quantum emulators, and we can also run these algorithms on smaller computers. If you take an example in finance, I think Pascal did a use case with Crédit Agricole, CACIB, where they were running an algorithm to evaluate debt credit rating and the evolution of this credit rating. And it can run on classical computer, of course, but they showed that with a quantum computer, a small one, they can run it 3.5 times faster. So it's not a quantum advantage because obviously this is a problem that can be solved by classical means, but it shows that there are small quantum computers that can already do better than classical computers on very specific problems. But as Henrik said, we're not there at the point of so-called quantum advantage. And this threshold of 200 logical qubits in most roadmaps is around 2029, 2030. So we're talking about, the next 5 years, some interesting stuff. Of course, roadmaps are always ambitious, so we don't know if it's going to really happen. But that's the plan now for the quantum vendors. Okay, second question. That's a question for you also, Henrik, specifically on the slide where you showed the partnerships. Where we have a unbalanced contribution of Fraunhofer. So you had lots of Fraunhofer logos on your slide because I think you had all of the different research groups of Fraunhofer. So the question was more, but are you really pushing research like Fraunhofer kind of stuff, or are you also trying to get these technologies into actual startups and corporate ventures?
So I mean, Fraunhofer has there like the big advantage, like in Germany, that they're often like at this intersection between that they're not like a uni more focusing on fundamental research, but they're really looking more into applied research and work there together. Then also with like clients, firms, customers to really reach these high technology readiness levels that I said in the beginning. And that is also what we are aiming to not create a just for fun. I mean, this is fun. I have to be honest, quantum computing is fun, but of course we also are in general looking here, how can this be implemented in the end at a client? How can we not only help develop this here as part of these European projects towards this demonstrator, but how can we then go further in this journey with you to bring this really to the clients to create a product. However, the funding that you get is here limited towards the industrial prototype level. So that is where this research project stops and where then we go the next step with it.
Thanks, Enrique. We'll keep the rest of the question for later on around our panel, as now we have our next speaker, Vincenzo, who has solved this connection, is able to now talk, but has also a very busy schedule. So we'll keep going with this presentation. I'll have introduced him already, so I'll just quickly indicate that he's working at the University of Pisa as a tenure track assistant professor, and he is part of the Emerge EU-funded project, and he will now present us the state of the art in AI. Vincenzo, the floor is yours.
Thank you. Thank you, Xavier. Can you hear my voice?
Yes.
Okay, maybe I can try to share my screen. Is that possible so that you can see my slides?
That's good.
Okay, 1 second. I'll try to go in presentation mode. Okay, now you should be able to see my slides clearly. Full screen.
Perfect. Thanks, Vincenzo.
Okay, thank you so much. So first of all, oops, what happened? Sorry about the delay. I arrived a bit later, and so I guess we had to rearrange the presentation. Try to do my best to provide some insights about the state of the art in AI with related advances and applications, and getting to the main, I think, argument that would sustain the need for quantum computers. So to essentially create a connection between AI and quantum computing. So this is definitely a short and incomplete glimpse over the AI progress and future challenges, but I guess it's useful for especially those of you that are not well into this community or research and are following closely the progress of this very important field. So in this very short presentation, I will try to cover these 3 main points. First of all, I would like to underline the increase in performance, in effectiveness on standard benchmarks that actually draw a lot of attention and pushed the entire community towards more and more complex challenges and providing solutions, real innovations that can then be used in more complex markets and sectors. Then I will try to suggest that this increase in performance is mostly due to the development of methodologies over the last few decades, starting from logic-based expert systems and getting to data-hungry machine learning methodologies and the deep learning revolution that is still being fueled today with large language models. And then I will conclude with this concept of scaling AI solutions with more compute, with more data, and what does it mean in terms of computational demands and new hardware, let's say, challenges. So starting from for the concept of AI evaluation, it is important to know that in AI, we've been always pushed with this idea of measuring progress through tasks also toy problems where we could have control over the rules that are governing them and properly compare different methodologies to understand what is better depending on different dimension of evaluation. Within image recognition, in computer vision, in natural language processing, in chess, this was a very important playground for those methodologies in the first days. And robotics, so with the concept of the embodiment and so on and so forth. I could name like hundreds of different tasks and settings, scenarios, use cases where AI has been tested and developed with a concrete platform that would put different researchers together with fun, creativity, and also with the ambition to do something that works in practice. And so benchmarks became the de facto standard to not only measure AI progress, but also to push the development, especially within the realm of machine learning, as we'll see. With the advent of large language models and foundational models, overall, this let's say firm ground has been shaked up a little, and we are seeing a lot of changes also in the way we evaluate AI solutions. But nevertheless, you can see possible comparisons between different models, large language models, visual language models that are compared across a number of benchmarks that would then still measure clearly the ability to solve reasoning or abstract tasks, the ability to code software, to solve mathematical problems, and so on and so forth. And what's interesting to note is that one methodology after the other, one step after the other, we have measured almost an exponential performance gains in standard benchmark. So it's very important to underline the fact that this is not a static evaluation context and has never been static in the entire history of the AI development. So we have always surpassed even human level capabilities on some tasks and then added new, more complex tasks that we wanted to achieve as the next step. So it's very interesting to know that we had an exponential performance gains even in the most complex of those tasks, and this seems not to stop regardless of specific methodology that we have used and replaced eventually over time. So this is a very good suggestion that we will continue, at least in the foreseeable future, to increase our ability to solve more and more complex problems. So you can see in this plot, for example, an idea, a clear depiction of what I'm saying. In the x-axis, you can see a timeline with the different years from 2012 that is pinpointed as the year of the deep learning revolution, when we had the ability to create an object recognizer, so a software that could recognize entities inside a picture in a very effective way, thanks to convolutional networks, deep neural networks. And as you can see, we have on the y-axis the performance related to the human baseline, that is the dashed horizontal line. And as you can see, different tasks here are depicted as different lines in this plot. Over time, we have almost always surpassed the human baseline. So it's definitely possible not only to reach human level performances in tasks that were even impossible to think to solve a few decades ago, that are now indeed very easy to solve with state-of-the-art AI solutions, even with capabilities that are better with respect to the best expert in that domain, from image classification to the understanding of natural language nowadays, competition in math problems, and I could name like 100 of different tasks for which this is the case. Thanks to this methodological advancement, we have seen also the application in several areas to create really innovative solutions that could be used to solve concrete tasks, mostly within the areas that I have mentioned, let's say, reported in these slides, but not only. So in computer vision, with object detection, in image classification, in natural language processing with translation, summarization, and now with question answering systems, in robotics, and now autonomous systems, in healthcare, finance, and so on and so forth. So it seems that there is no sector, no market that is not touched by this AI revolution. As you can see in this slide, I try to summarize the global artificial intelligence market as billions of dollars and categorized by solutions, so services, software, and hardware related. And as you can see, it has almost an exponential growth predicted over time with a 36 compound annual growth rate. If we take a look also at the end use sector, we could divide the 2023 196 billion market of AI applications in different and let's say well divided areas: advertising and media, bank, finance systems, healthcare, automotive and transportation, manufacturing, retail, agriculture, law, and others. So we have a very pervasive integration of those solutions into our productive infrastructure. But what made this possible? This is the main question you may ask at this point. Well, this is mostly due to the evolution we could fuel as scientists in terms of methodologies behind, under the hood, essentially. So we started with expert systems and with this idea of describing the world through a set of facts and rules with a formal language, logic. And from this basic assumption, rule-based decision-making systems, later called expert systems, born. So the idea was to talk to experts, like, for example, a doctor, and asking her what are the main rules that would describe your reasoning and your decision making. And then after a lot of those questions, we could gather all these insights and code them with a formal language to do logic inference. So with a new pathology, being able to diagnose it as a doctor would do. That's really powerful, but in the end has a limitation. So the impossibility to scale in terms of effectiveness and the requirement of strong contributions from domain experts. The transition to machine learning, that is data-driven models, has created an opportunity, an incredible opportunity for our field, I would say. So with the ability to process automatically data, to infer, in a sense, these reasonings without intervention of human experts has become the pivotal change in AI. And first, the statistical methods and, let's say, sound probabilistic reasoning models were proposed, but only later we even abandoned more and more formalism in favor of, let's say, neural networks and models that are less likely to produce sound and complete answers to your problem, but in practice are very powerful. So at this stage, neural networks emerged as a strong methodology that would provide, let's say, a single access point to a set of possible applications in different areas. So before the advent and the development of neural networks, it's very difficult to develop a single model, a single AI agent that could tackle multiple tasks. We had several specialized solutions for different applications. And neural networks essentially are the foundation of deep learning, which is just expansion in terms of scale of this methodology. What is the real power of deep learning with respect to classic machine learning then? So this idea of processing directly raw data, so being able to learn machine learning solutions, AI solutions directly from data. Because in the early days of machine learning, yes, we would definitely start from data and let a machine to learn by itself how to solve a task, but we would still need a data scientist, an expert, to figure out what would be the better way to describe concisely and richly those data. So for every different task, we would have needed the contribution of an expert of that domain, or a data scientist that would take charge of exploring different ways of representing numerically a problem. Now with deep learning, we have a completely end-to-end, this is a very well-known keyword in our field, end-to-end solution, starting from data and producing a relevant model that can then be used to solve a particular task. So in this image, you can see how, I don't know, a picture of an image with these pixels is just processed as an input to a neural network that then, after a bit of crunching of numbers, is able to provide as an output the label, the identification of the object contained in this image. For example, if it is or not a car contained in it. And by the way, neural networks are not that fancy, they're not that complex as it seems from the news. So they're just graphs. We can depict them as directed graphs with weights that indeed would weigh the contribution of different piece of information that is propagating inside this network. So we could represent, for example, an image as a set of pixels, and those pixels would represent the input layer of this network. So x1 is the first pixel, x2 is the second pixel, and so on and so forth. And then what we would do is just have a linear combination of those pixels that would produce intermediate representations inside some hidden layers of this network, and then eventually combine again these partial, compressed, and elaborated information to produce the relevant output. The magic maybe behind all of this is how those different weights contribute a different piece of information, integrate them, are learned in a completely automatic way. And this is the magic of machine learning and optimization, numerical optimization, I would say. So the rise of deep learning that is more often, as I mentioned before, identified in the revolution in object recognition and computer vision is mostly due to advances in the neural network specific architectures, the convolutional neural networks, recurrent neural networks, transformers, that are just adding some very little insights to these very basic directed graphs we had seen before. And this has led to, after a lot of engineering, mostly to superior performance with respect to any other methodology explored within development of AI. What we could say definitely is that this success was mostly due to three factors that were not present in the past. First of all, the availability of hardware, and we come down again to this very important topic for the workshop. Why computation and new hardware capabilities are not only making things more efficient, but are enabling factor for the new wave of AI solutions. Then a second element is the big data availability. So after 2000, we had access to a tremendously bigger amount of data of any kind, of any structure, structured data, unstructured data, multimodal data. And finally, a robust software ecosystem and talent pool. The research community grew significantly, exponential. So the number of people that can actually learn, teach, and develop AI solutions has grown tremendously, along with an ecosystem that would support the easy prototyping and implementation of those solutions. With this, I just want to touch down on the last part of my intervention. It is about the neural scaling laws. So in case you are interested in the scalability of deep learning and what it means also for large language models and all the innovation we are witnessing today, you should look into neural scaling laws, where essentially we try as computer scientists, as research scientists in AI, to better describe, theoretically describe, or empirically describe the relationship between model size, data, and performance in large language models, foundation models. How we can predictable understand what to, let's say, improve in order to increase the final performance. And there are a lot of empirical studies about this, and of course, we witness a lot of developments over time with respect to those concepts, ideas, and theories. I just wanted to stress out the fact that this is something that we are witnessing right now. So in 2020, for example, we had a lot of researchers interested in understanding how we can directly improve the results by increasing the model size. You have listened, let's say, heard a lot of times talking about these multi-billion parameters that would be contained inside these large language models like GPT-3 and 4 and then 4.5. So essentially there, the focus was, let's increase as much as we can the model size of these neural networks parameters and the data set on which we train this system. With the idea, bigger is better. The emphasis again was on the parameters. Then on 2022 and later till 2023, let's say the chinchilla paradigm, the post-chinchilla area determined a shift in the focus, not just increasing the amount of parameters, but also focus on the data quality and amount. So the more data you add, the better your AI solution is. And finally, from 2023, we have witnessed a strong shift of focus. So we are not able to create models that are just bigger and better. You have seen the, I say, the failure of GPT 4.5 that is not better than the O1 model or other reasoning-based models. This is because we are now focusing on scaling the performance, but after the training phase, during the inference phase, so spending a bit more money during inference, letting those systems reason and develop their understanding after training, while we are using them essentially for our specific purposes. So what we are witnessing, unfortunately, is also an exponential growth, not only in effectiveness and the size of these models, but also in terms of energy and costs, and the infrastructure demands are growing highly as never before. This is also some environmental and economic considerations to do. And here in this plot, just show a very interesting graph. So we are in a log scale here. So this apparently linear growth in the end is exponential, where I show over time how the cost to develop this model is growing. So the cost is on the y-axis. As you can see, we are getting from about 10K in 2016 that would take in order to develop a state-of-the-art AI solution to about 100 millions in 2024 with the latest and greatest AI solutions spinning out from big corporations. So this is worrisome for some, but also very interesting on some other ends, since we are still able to increase significantly the effectiveness of this solution, tackling more and more tasks and with better proficiency. We are also able to scale in terms of computational capability. So every couple of years, let's say the Moore laws suggest that we would increase double the size of computation, furthermore with the large language models. So how we can fuel this constantly increase, exponentially increase in computational demands that would support the next generation of AI models, I say we need a bit of a change of paradigm also in the computational framework and hardware that would support it. So this is where quantum computing is promised to be, let's say, a relevant solution. So I hope in the future we'll see more and more developments in this area where notably we are still a bit behind in terms of developing the software ecosystem and early pioneering results to make those systems work in practice in that on that hardware essentially. So this more or less concludes my overview view on AI. I hope I convince you that the AI field is growing and doing its work in trying to provide more and more effective solutions. There's no indication that this would stop in the foreseeable future. So I hope this incentivate also the exploration of different methodologies and computational infrastructure would continue supporting this vision. Thank you so much.
Thank you, Vincenzo. Very nice presentation of the challenges and overview of AI. There are two questions. I don't know if you have time because I know you are a bit in a rush, but I'm happy to.
Yes, maybe
Yeah.
I can take a couple.
Yeah, there are two which I think are quite relevant from Desiree. Thank you very much. The first one is about learning AI if you're an engineer. Does it really make sense to learn the basics, the fundamentals of AI from the ground up now that AI itself will be able to code and develop its own models? And in fact, the future seems to be more into AI integrator rather than AI programmers. So what's your take on that? Should we still study AI at the basic level, or are we all doomed to be AI integrators?
No, I think honestly that in terms of specific knowledge in AI, this is still highly required, and I think a specialization in AI is definitely useful for the next decades. So I'm not really worried about this. I wouldn't be worried about this, but maybe more about the lower, let's say, engineering aspects at education level in computer science. That I think needs a rethinking. So I don't know if you are focusing on software development, something there needs to change also in the way we teach and we learn about how to write software. Nowadays, you have seen more and more news talking about, let's say, the need, let's say, the replacement of software developments with agents that are specifically designed to develop software. And there is a field that is a bit more structured, where an application where AI solutions are doing a very nice job. I mean, they are very good in what they do. So there, for example, I would a bit more worried. But in terms of learning also the basics of AI, I would definitely still suggest it, even if they are about methodologies that nowadays are not mainstream, but are very useful to understand. As you know, the research is also a lot cyclic in a sense, are very interesting to the future developments in this area.
Thank you, Vincenzo. And second last question before we move on to the next presenter. So the AI space is heavily dominated by US and China. Is there any space for other players in Europe, Africa, Latin America? And could the solution be to focus on data, meaning looking at specific data to feed models, build very specific AI systems more adapted to these other countries?
Absolutely. So I think that maybe now more than ever, this is becoming a positive reality, because in the last few years, let's say since the birth of OpenAI, just to mention a key player, AI cutting-edge developments were, in a sense, done within closed doors, so within private companies, with these let's say secretive development. But now I think we are in a very interesting time where we will witness the emergence of an open source ecosystem for AI. So a lot of open source solutions, models that we would need to control, orchestrate, and use to build our own solution. So you see, I see a very interesting period period of time where this will be much more open and also available to different communities, not just within specific countries as it's been mostly so far. And then I see another opportunity, connected to a strong need. As you can see now, for example, governments like US are advocating for a more isolated development of those methodologies and connected innovations, products. So now in Europe, I can feel it. There is a strong, let's say, will to develop our own, let's say, proprietary or still, let's say, trustworthy AI solutions that are spinning out from our ecosystem, from our European ecosystem, and so on with other countries. So every country will have, by the very need of it, since it will enable, let's say, very key services, their own ecosystem. And at some point, we will need to dialogate better with a more holistic approach at the worldwide level. I believe, like it happened also with the internet and the web, if you think about it. So I think that we will see over time strong commitments for also local governments and different communities to participate more. And this will create a lot of interesting opportunities for companies, organizations at any levels to participate to this dialogue. Maybe it's a very positive interpretation of what's happening, but I believe we can make a contribution towards this vision.
Thank you, Vincenzo. Thanks again for joining this panel. It was great
Thank
to
you
have
so
you
much.
here.
Sorry again for the delay.
No worries at all. And good luck with the
See you.
continuation of the Emerge project,
Thank
of
you.
course, which is a great AI
Thank you.
project
Thank you so
funded by the
much.
Commission. Super.
Thank you.
Thanks again. And we are now moving on to our third presentation of the day. Anastasia Shilova, who is a task force lead in the market and legal lab at Cyberinnovate. She's also a legal expert at Cyberinnovate. As you probably know, Cyberinnovate is one of the main partners in the USAID projects, and it's a startup studio based in Ukraine. Anastasia specializes in digital law, compliance, and tech business regulation. So in practice, she helps companies implement effective compliance strategies and mitigate their legal risk in the digital landscape. Anastasia, the floor is yours.
Hello, everyone. Nice to be here. And today I try to explain the AI Act in simple terms. Do you see my presentation?
Yeah, looks good.
Okay, thank you. As I mentioned before, today I'll try to explain the AI Act in simple terms. And you can leave your question in the chat box along with your email, and I'll do my best to answer them later. Today, a lot of people discuss this new rule, this law that has already been adopted. It already affecting the business and cannot be ignored if you work with AI in Europe or serve European clients. What is the AI Act in plain language? AI today is everywhere: chatbots, requirement tools, facial recognition, text generation, even medical decision support, but also it is deepfake, fake news, emotion tracking in school. On one hand, it's progress, on the other, it real risks, and AI became widespread and hard to understand. So Europe decided to act and to adopt the AI Act in order to not block innovation, but not allow AI to undermine human rights, dignity, democracy, as well as of the European Union. And this law does not say all AI is dangerous. It says let's assess the risk, and as higher the risk, the stricter the obligation. So what is AI from a legal perspective? According to the regulation, an AI system is a machine-based system designed to operate with varying levels of autonomy and that can, for explicit or implicit objectives, infer outcomes such as predictions, content, recommendations, or decisions that influence physical or virtual environment. So AI is machine systems that can infer outputs like predictions, decisions, recommendations, or content based on data. It includes machine learning, logic-based, and rule-based approaches. And it recognizes adaptivity, the ability of the system to evolve after deployment. Next, I offer to talk about who does the act apply to. Sorry. Yeah. Many people say we're a small startup. This doesn't affect us, but actually it does. It applies to AI developers. Companies, they integrate third-party AI into their product. Anyone placing AI systems on the EU market, even if based in the US or Ukraine, for example, even open source systems, if you fine-tune and commercialize them. The regulation has the extraterritorial scope, and that means even if you are outside the European Union, but your AI is used within the European Union, you must comply. The AI Act classifies AI systems by risk level. The highest is a prohibited risk, which banned outright. For example, social scoring, manipulative AI, biometric categorization based on sensitive traits, for example, political views or sexual orientation, emotional recognition in schools or workplaces. Next level is a high risk, which tightly regulated. For example, it is HR systems, medical diagnosis tools, school assessments, AI in justice, finance, or infrastructure. These systems must have strict requirements, transparency, documentation, and risk assessment. Next is limited risk. For example, chatbots, generative AI. In such a case, you must inform users you are interacted with AI. And last but not the least, minimal risk. Example, spam filters, and there no regulation applies. What does the AI Act require from high-risk systems? The regulation introduces a clear set of obligations for high-risk AI systems. These are grouped into 4 main categories. The first is assessment and registration. These are the preconditions for assessing the EU market and includes conformity assessment, which means verifies that your system meets all regulatory requirements, and registration in the EU database, public listing of high-risk systems unless used solely by public authorities. Next is risk management and human oversight. This ensures ethical and controlled deployment as implement a risk management system across the entire AI lifecycle, and also ensure human oversight, which is defined who can intervene, how, and under what circumstance. Third is data governance. This guarantees fair outcomes and compliance with anti-discrimination standards. It includes ensure data quality. The data must be relevant, representative, and free of bias. Document how data is scored, cleaned, and processed is needed too. The last one is technical documentation, logging, and transparency. This builds trust and accountability. Provide full technical documentation is needed in this stage, like purpose, architecture, function, safety. You also need to keep logs to enable audits and traceability, and ensure transparency, which means clear instructions and notifying users they are interacting with AI. Exemptions from these all rules is apply for scientific research, military use, and national security. Let's talk about money. What are the penalties under the AI Act? There are 3 levels of violation, and each with different fine. Prohibited practices like using AI for social scoring, manipulative behavior, or biometric tracking in public, and fines up to 35 million or 7% of global turnover, whichever is higher. Next is non-compliance with obligations, and it means failing to meet responsibilities as a provider, importer, or deployer, and or violating requirements for high-risk systems. Fine up to 15 million or 3% of global turnover. And third is providing misleading or incomplete information, such as supplying false of partial data to authorities or notified bodies, and fines up to 7.5 million euros or 1% of global turnover. Startups and SMEs benefit from whichever is law rule, either the percentage or the euro amount, and this protects economic viability while still enforcing compliance. Sounds serious, it is, but there is a good news. You don't need to do everything at once. And the AI Act is phased in gradually, giving businesses time to adapt. The real question isn't, are you ready now? It is, are you already moving to the right direction? Let's look at the AI timeline. In July 2024, the AI Act officially enters into force across the European Union. On the 2nd February 2025, prohibited practices must stop. From 2nd August 2025, obligations for foundation models began, even open source models used commercially. And from August 2026, full compliance is required for high-risk AI systems such as HR, education, finance, healthcare, public service. So while full enforcement is still a year away, we need to start preparing today. And what should businesses do now? In my advice, it's like audit AI systems. Identify what qualities as AI under the AI Act. Next is assess risk level. Use Annex 3 criteria. If it's high risk, start the compliance process. Check for personal data biometrics involved. Next is create a simple AI risk memo, like a short living document covering your system's purpose, data, architecture, logic, updates, and safeguards. Start your documentation, algorithm, models, safety instruction, and risk controls. Where applicable, run a human rights impact assessment. Next, you should train your team. Even not technical staff should understand how your AI affects users. Next, implement explainability. People need to understand why your system makes decision. Also, it's good to be prepared to audits, because if it not now, then can be soon. And also use a regulatory sandbox if it's available in your country. Also, I would like to underline challenges businesses face under the AI Act. As we said before, it is a strict limitation on real-time biometric identification and categorization based on sensitive traits, example, political beliefs, sexual orientation. And documentation load, high-risk system must provide full technical documentation, training data, decision logic, safety layers. Next is explainability. You must explain your system's reasoning to users and regulations. Responsibility. With the new product liability directive, the burden of proof is on the provider. You must prove your system isn't defective. Next is compliance isn't cheap. So it involves risk control, external testing, training, and policy decision, and man-hours cost. Uncertainly, the law is adopted, but many technical standards are still being developed, and we are waiting for it from the May 2025. And there is also a gray zones, like fine-tuning open source, you may become a provider. Writing a script, probably not. It's complex. And AI toys or education, it's high risk. Or self-driving cars, no, because they fall under another directive. But there is a few positive points too. Legacy model advantage, it's if you AI was deployed before the AI Act entered into force and you don't significantly modify it, it's not affected yet. Also, support for innovation is a positive point of this Act too, because regulatory sandboxes and R&D exemptions are included. For startups, fines are less. And next one is AI literacy is empathized, which means the European Union highlights the need for training, and not just for developers, but also users and affected individuals. And what final thoughts I have about all this presentation? Yes, this is tricky, but let's be clear. It doesn't ban your product. It doesn't block your market entry. It doesn't ask you to, it does ask you to prove your system is safe, fair, and explainable. And if you can prove it, you win. Custom will trust you. Partners will work with you. Government can buy from you, and investors will take you seriously. So thank you for your attention, and I'd love to continue this conversation on the project or on LinkedIn.
Thank you, Anastasia. And as we discussed, the best, if you have questions specifically directed to Regulation AI Act, is to drop Anastasia an email or write your email in the chat. We'll
Okay.
also have some discussion around AI during the panel, which is going to follow immediately. Thank you, Anastasia.
Thank you.
So I'd like to call back in the video, Henrik, and new speaker, Nuria. Welcome, Nuria.
Thank you very much.
This is our final panel for today, kind of a wrap up, and we are going to try to also address a few unanswered questions in the chat, so we're not forgetting those either. So maybe starting with you, Nuria. First of all, we haven't introduced you yet, so I'll say a few words, and maybe you can complete that with what you do currently with AI. So you're a computer science engineer with a master's degree in big data and analytics. Specialization is in data science. You've also done some MIT certification in quantum computing, so you actually know both, as well as quantum computing application, specifically in cybersecurity, chemistry, and optimization. You're currently a data scientist at INECO for the Spain's Ministry of Digital Transformation, which means that you are going to be working on AI-powered solution. Can you tell us more about what you do now? And in particular, I'm interested to understand what you see as the main obstacles for companies to implement AI in their processes.
Yeah, thank you very much, Sergey, for the introduction. Yes, in the Ministry of Digital Transformation, I'm in the AI group of people that we are like trying to analyze the risks and evaluating projects. And also we are very in contact with regulatory sandbox that is being developed in Spain. And this is our main work there. Regarding the question about the main obstacles that companies are facing when they want to implement an AI solution, I think it's a very good question, no? Because first, if we are talking about startups or small, medium companies, we need to empower the company's employees through the training of these technologies, no? Because difference that a big company, they have specific employees that know how to develop these things, and small companies needs to specific train their workers. So that's, for me, it's very important to join with experts that know how to train the people. And also another obstacle that I think it's the access to data. No, it's sometimes it's very limited, or the quality of it's not good enough to develop the solutions that they want. And cost, of course, cost of developing solutions can be very expensive, depending on the cloud solution, that the cloud system, sorry, that you're choosing, or the way that you are storing the data, the costs can increase. And also it's very difficult at the beginning when you are developing this kind of solutions to get the sense of the what are you getting, if you are doing it right, if it's going to give you benefits in when you're doing it, no? So I think that for this kind of companies, it's very important to look for open source resources like Hugging Face or PyTorch or TensorFlow, because of the large community that exists behind them. And also to join forces with academia and researchers, because I think it can give like to ensure the rigor and the ethical overviews when you're developing a model, for instance. They can give you the expertise that maybe you don't have in the company. And also talking about like Europe and what it's been doing here to help this type of companies, I think that the creation of the AI factories that now it's happening in Europe, it's super important, because it will help the small and the startups and the small and medium companies to have access to some resources that maybe alone they couldn't afford to have, no?
Thank you. So if you look at the companies you've helped so far, do you have a specific example of a company that you know, with the Ministry of Digital Transformation, you've been able to help with AI processes? Does that rely on specific experts from the government, or are there particular resources that people can tap on, other than, of course, open source as you discussed, but other type of AI integrators or AI accelerators that you can also use to help with your progress?
Yeah, well, actually, in the government, we have the ENIA, the National AI Strategic for the government, that it has like different parts of it. One is more for agriculture, and one is more for cathedrals, for universities, and it has different actions that and grants that help companies that applied for them to develop the systems. No, then there is a team of expertise that help to make sure that the projects are being done properly, that are in track, and the role of the government is more to follow them with the companies that are developing, that get the subvention, and to make sure that we arrive at the goal that we all want.
Excellent, thank you. So Hendrik, we know you from the previous presentation. Thanks a lot for the great presentation. In your job at Capgemini, I'm sure you see a lot of companies working with their quantum strategies and quantum applications. We discussed already a little bit the fact that the real quantum computers, the ones that are industrially relevant, are not there yet. What will it take to get there? So in other words, what are the technical things needed to build those large quantum computers that will solve real problems?
Yeah, so in order to be able to build like large quantum computers, like a key challenge that we have to overcome here is the noise of the qubits, or the quality of the qubits that we currently have in the systems. So we're currently in an era of the noisy intermediate scale qubits. So basically, one can imagine that every quantum bit is very fragile. So we are now like used from our computers that we want to know if is it 1, is it 0, and we get a very precise value there. We have very good error correction here already. But this is something that quantum computers, for them, this is still a challenge, because every qubit is affected a lot by environmental impacts. And what we need here is a high quality of qubits, or very good a very good error correction of these noisy qubits that we have. And this is a challenge here, because in order to do these kind of corrections and to create like one very good qubit, we need a bunch of qubits currently. So the question is, when will we arrive towards a state or a quantum computer where we have not noisy qubits anymore, but so-called fault-tolerant qubits, fault-tolerant quantum computing? When will that arrive? And I think what is needed there from the not only from the technical, but maybe more from the societal challenge also to understand, is that there's still a lot of investment also needed into quantum computing, into the different hardware types also of quantum computing. Because we are right now in this very interesting age where we have multiple different hardware types, and we still will see which hardware type will be best for which kind of problem, which kind of solution. And I think that we might be closer than some people think towards the state of this fault-tolerant computing. I think we've heard it also in the last months and weeks, also like in the news. I think everyone has heard like these big announcements by companies like Microsoft or Google, where they have like made steps forward. And I think at some point we will have a similar moment as an AI, where suddenly it's there. It's there to use, and we have the hardware. And we need to be prepared for that. We need to be prepared now already by developing these algorithms, as I said earlier, to be ready as soon as the hardware is ready to use it, because that is what will give us competitive advantage also, to be ready when the hardware is ready. And I think, yeah, there are a lot of challenges to overcome, but also a lot of exciting developments in the field that I'm looking forward to.
Very, very interesting, and that actually echoes with a few questions that were asked previously, so I'll bring them up into that particular point. You actually touching on a very important point, which is that there needs to be investment in these quantum modalities and the different ways of getting a bigger, more error-corrected quantum computer. And one of the questions in the chat was, why are we investing in this? Because, we are just Europe, and US are, of course, quite good at it, probably better than we are. And maybe we should focus on something which we're good at and which is more simple to reach already now, which is quantum sensing. And before I leave you the floor again, Henrik, I think from my perspective, as an analyst helping companies to get funded, to get financial rounds of funding, I think when we look at quantum sensing, we see it as a smaller market. It is a smaller market than quantum computing or quantum communication. So it's kind of natural that the bulk of the money goes to quantum computing compared to quantum sensing. But I wouldn't say that Europe is behind the US, and at least not in terms of quantum computing. We have the talent. Actually, if we look at the number of graduates from programs related to quantum technologies, we have twice as many as the US, which is quite significant. We also have some fantastic role models, Nobel Prizes like Alain Aspect, who've done quite amazing discoveries over the past 40 years. And we have the companies, we have the startups. I mean, there are a number of really exciting European startups which are building the different modalities. Only in France, you have a leader in neutral atom computing, another one photonics. So there are a lot of interesting technologies out there. And I would say that, as exactly you said, Henrik, we have to go to the AI moment. So essentially, today we need to invest because we should ask ourselves the question, where would we have invested in AI 5 years ago if we had known it would be such a big hit? Well, that's exactly a question we have to ask ourselves today for quantum computing. And we cannot wait, because otherwise, as the person asking the question correctly said, it will be China and the US winning the race. What do you think, Henrik?
I can just fully agree with what you've just said. I think it's like really crucial. Like we've seen this in AI, as you saw, like this big advancement in China and the US, and there, I think one can say Europe is still a little bit behind those developments, and we should make sure that in quantum this does not happen. And there it's crucial that we invest here in Europe in quantum, and that we do not just rely on the US as a partner that would somehow give us the type of technology. I think that is also like becoming more increasingly clear in the overall European landscape, that Europe itself needs to make sure that key technologies are also developed inside Europe and are part of the European ecosystem. And this is something that can only be done also through this investment, through funding. I think one can also look back into the history of the semiconductor industry, also when it was built up in Japan or in Korea. How was this done? By government also supporting these developments, by supporting the growth of these industries, because that is what is needed to like kickstart this kind of revolution. And here the quantum revolution also that should be here in Europe. So there, yes, of course, the US is with us at the top, I would say, but one should not be disencouraged here, like especially as you said, with Pascal and in France, or like other hardware startups we also have in Europe, like IQM or like AQT. Like we have a bunch of hardware startups that are also taking a very different approach from the US. And as I said also before, it's not clear which one is the best, or I don't think there will be just one single best one. There will be types of problems, types of solutions for different hardware. And I think that's the beauty in Europe, that we have this strong ecosystem. And this is also something I see in my work, that we have also people, partners from Japan or Korea that like create a German or European entity somewhere here to be part of this ecosystem that we have, and to also help to grow us here, to develop. And I think this in general is also a very good thing about the current development in the European programs, that we start to also look how can we incorporate here also good technology from other partner countries that can also be funded through, for example, the Horizon program or like other programs in general. So yes, we're not behind in Europe. We are riding the wave, and we are at the front, and we should stay there. We're continuing to invest and continuing to develop. That's
Before we go back to AI and Nuria, I just want to wrap up on this topic, which is very critical. You correctly pointed it out, Henrik. This is a matter of strategic sovereignty. So I don't think there is a choice. It's not like we can just focus on sensing and that would be good enough. No, Europe needs to dominate also quantum computing and even quantum networks. There's a lot to be done. And of course, the bottleneck is always financing. Clearly, the US has access to larger amounts of capital. There was a question in the chat around, why is there only quoted listed companies in the US and not in Europe? Well, that's a consequence of the US market being better in terms of accessing investors. And that's why you see Rigetti, IonQ already listed with enormous valuation, by the way, because when you see a company like Rigetti, great company, by the way, but still doing 10, 15 million euro revenues and valued at 3 billion, there's probably a little bit of anticipation, of over anticipation of what quantum can do. It will get there, of course, at some point, but should the value should be there already? Maybe, maybe not. That really shows the US has definitely a lot of money there. In Europe, valuations are more conservative. I mean, the best quantum companies probably have valuation between 500 million and 800 million currently, which is still really nice, but it's not the level that we can see. However, the good news is that these companies are selling. There are companies in Europe, you mentioned their names, IQM, AQT, Pascal, who are selling quantum computers, even small ones, to HPC centers, to even to corporates. I mean, Aramco is buying a computer from Pascal currently, and that creates revenues. So there's already some traction there. So I think the answer to that question is there will be companies going IPO also in Europe, potentially. Maybe not this year, but within the next 2-3 years, I would bet that there will be a few of those companies that have reached the scale and the momentum to be able to be also quoted. Now, of course, they could decide to be quoted on NASDAQ instead, because that's always the bigger market. But let's hope that they will also consider the European stock market. All right, going back to AI. So AI is definitely on a roll and already showing real applications compared to quantum, which is still, with not yet industrial applications, which are fully relevant. But we also see, and especially over the past 2-3 years, that generative AI has dominated the headlines. So it's just this technology has taken the world by storm, and now everyone understands the potential of AI through that. But isn't that a bit restrictive? Because in the end, AI is much more than just generative AI. And in your eyes, what are the useful applications of AI, the ones that can really have an impact on the planet?
Well, from my point of view, I think the first question I have is there any field that really cannot get the benefit of using AI? So because I think that it can be applied to all kind of fields, and all of the fields will get an a huge improve using the systems. But you have to focus in some fields. I would say healthcare for sure. I think applications in healthcare are game changers, like enabling early diagnosis, personalized treatments, and remote monitoring. It's super crucial. Then financial services as well to detect fraud, for instance, or risk analysis. And then in logistics, of course, with like inventory management or optimization of routes, which is also quantum computing also has a role in this part, because there's a lot of simulations to try to solve these issues. And then there are other fields like agriculture or education that AI can help having a big impact, in solving things in that fields.
Thank you. So from a planetary impact perspective, do you see a challenge where most of the AI resources, which are scarce, because in the end it's GPUs and they cost energy and even water in data centers to cool them, do you see that those resources could be moved towards something which is not that useful, generative AI style creative content and things, instead of being used for more impactful and important application? Is there a risk? Are there solutions to this energy crisis that will be created by AI?
I don't really get well that. So you think if that using generative AI, for instance, can help in reducing this cost in energy
I would say
consumption?
more
Or...
it would be spending too much resources on generative AI, which is not really bringing a lot to the world. Maybe some is, but maybe
Well,
less than
actually,
machine learning, which could be solving big problems.
yeah, actually, generative AI now is it has get very lot of attention because the way of the content is created, like images, videos, and everything, and that is why it's so impactful right now. But actually, generative AI also can be done like in drug discovery things, for instance, that has more impact than content creation, for instance. And the sad thing is, this part of the generative AI is not as shown as the creativity side, maybe to say it, no. So I think that they are already investing these technologies to solve these kind of problems, no. And yes,
That's
so Yeah, sorry.
That's a good point. No, yeah, I think you shouldn't corner or restrict generative AI simply to you know, I don't know, creating stories for your children. There's a lot more you can do with Gen AI, and foundational models can be used for many things. In fact, recently I was talking to a company in healthcare, radio X-ray analysis company, who is building foundational models. So they are using generative AI also for their solutions. So it's not only about machine learning, but as you say, generative AI has captured the headlines because it's easy to understand. People can use it. They just have to spend €20 per month at OpenAI or some other solution. They are free ones as well.
Exactly, and you get wow results like in
Yeah.
seconds. But it is
Exactly.
done also like just predicting protein structures and simulating chemical reactions. But
Yeah.
this is not as visible. It's not attractive as the other.
So on this subject of healthcare, and I'll bring in Henrik in the conversation. This is an interesting one. Protein folding has been demonstrated by AlphaFold, which is essentially an AI, and it's been very performing very well for this. We also know that we will, in the end, be able to do that with quantum technologies, but we're not there yet. So what's the future of drug discovery? Is it AI? Is it quantum? Is it both?
I would think it's both. Like if we mix quantum machine learning, I think that would be the change maker. Because I also thinking in sustainability, no? Maybe if we can train models way faster than we do with conventional machine learning, the energetic cost, the training these models that we are having now, if we use a quantum computer, having in mind that the cost to use energetically those kind of computers are good enough. So maybe the fast way to train these models can help also in reduce, first to getting faster results, and also to improve the cost of energy that we're having now, no? In a sense of sustainability.
I would agree.
Henrik, what's your take on quantum
I
AI
would
in
agree.
healthcare?
Yeah, like the quantum and AI, like great combination for healthcare. Maybe to add to the points that Miri also mentioned, I think quantum can also help us to make their more accurate predictions for these AI models to really increase the accuracy of the data that we can get out of it. And I think this is like a great example of that. Yeah, the quantum and the AI revolution, they're not like two separate things, but it's like something that's happening together, where one cannot like look at just one or the other. But the same way the quantum machine learning can have an impact on AI development, the same way the developments in AI help us to accelerate the development of quantum computing. And that's very nice that one has there these synergetic effects that we're going to start to see hopefully soon in industrial applications and so on. So I'm really looking forward to how these technologies will merge together.
An interesting example of this is companies using quantum-inspired algorithm to compress AI models, large language models. I think it's the case of a company called Multiverse. And I think that is an interesting issue. It's essentially using quantum to do AI better, or quantum principles. And we know that, of course, in AI, one of the biggest problems is the cost of training these models has completely exploded. We're talking about billions of dollars used, thousands of GPUs used to train those models. So anything we can do to compress them will of course, have a huge influence, not only on the economic side, but also more importantly on the energy cost, which means, of course, CO2 impact of these technologies. Super. I think we are almost out of time, so we can maybe finalize our the next 5 minutes of discussions. And I'd like to go back with Nuria on a topic that we touched on with Anastasia, which is regulation. Because if you look at the spectrum right now, you have on one end the US, where, well, everything is possible. There's the Wild West, and there's not really any regulation. There will be even less now with the new administration. And on the other side, you have China, where it's completely government controlled. And if you have a tool like DeepMind, I mean, probably it's been trained to tell you certain things about certain events that may or may not have happened in China. So in the middle, you have Europe squeezed in the middle, and of course, coming up with some way of regulating the AI Act, but often seen negatively by other players. So what's the right solution there? Should we follow the European way, or should we go to the US?
That's an amazing question. Now, actually, I think that what the AI Act wants is to emphasize, the the transparency and to build trust between the citizens that will have to use or will like the systems will decide on some things that will affect the society, no? And actually, if we see Spain, for instance, the European the AI Act that is based on risk levels. If we see the projects in Spain that belongs in the high risk projects that are the ones that really needs to be regulated and to be transparent and to be able to specify how they are getting the results and everything, it's only 10% of the projects that are being developed in Spain. So the rest of the projects are don't have this charge that the high risk have. Although it's always recommended to develop to follow what is known as the ethics by design when you design an AI system, like to embed when you are designing it the ethical principles, no, to make the projects trustful and as transparent as possible. But I think that it's really good to have some kind of regulation. I know that lately the United States government, there are some pressures to make Europe be less restrictive, and there are like the regulators are kind of scared to do it because of this. No, how you ensure that there are not fake news, how you ensure that the systems are not malicious or whatever. No, so I think that we are in the right point. But it's true. It's giving the sense that it makes innovation go slower. I was at the last Mobile World Congress, and actually the feelings with the developers was that this type of regulation makes the innovation go slower, as I said.
Yeah, so I mean, clearly this is a key issue with the AI Act. I think the Anastasia presented it nicely, explaining also that it depends on the technology you're pushing. I mean, there are technologies which are sensitive, AI used for certain high-risk tasks, which of course have to be heavily regulated, while others don't have to do that. But the basic principle of the AI are very healthy. I mean, shouldn't be any bias in the algorithm. You should understand how it comes to its conclusion, etc., etc. So it's kind of common sense. The challenge is to put it into a regulation, and of course there is always the risk of over-regulating. But in the end, I think if European companies can adapt well to this regulation, they'll have a huge advantage over their counterparts. But in the end, we are the largest market in the world with 400 million inhabitants, and this is another way to protect it. I mean, we're talking about tariffs right now coming between the US and Europe. And tariffs, of course, are always hurting the consumer. In that case, if you create a regulatory barrier like this one, you make the world a better place, or at least Europe, in terms of AI, but you also protect your own companies. Of course, it comes at the cost of maybe making it a bit more difficult to develop. But I think here there is a middle ground that the EU can take in regulating without overburdening the companies. All right, maybe final question for Henrik to close the day. You are part of a very exciting European project, Equality, which is really working on next generation algorithm for quantum computing. If you are a startup from the UA Seeds ecosystem and you want to join such a project, I mean, how do you get involved into a European project like Equality? What do you have to do? What do you have to look? What does it require?
What does it require? I mean, first you need to have good technology, good ideas, and I think, I mean, I am like speaking maybe more from our perspective. So we go to trade fairs, to the EQTC, to like conferences where you can meet other people from the ecosystem, and usually like that is the first way to go, like check out like who else is inside the ecosystem, who do you think could collaborate, who could benefit also from the solutions you provide, where could one see a business case. Of course, there are also then like different events depending on the calls where people come together. They can organize together, a call is presented, and then you can organize their consortium. But also you can approach already existing consortiums or partners also there where you think, for example, in equality or this use case, we have something very similar. Maybe let's build upon this. I think that is always a great way to see like what is out there and to help to provide their more advanced solutions. Yeah, maybe that's from my side, but I think you also might have some insights there, Xavier.
Yeah, I mean, so you're completely right. And like, I think in the end, there are multiple call for proposals, which the European Commission is offering every year. And many of them in the quantum and AI space, which are seen as two critical technologies. So it really depends on the level of maturity of your technology, because there are different instruments adapted to different types of maturity. If you're still in the lab phase, in the research and development, there are instruments typically funded 100% by the Commission. And if you're closer to market, closer to the prototype stage or demonstration, then you have other instruments which are more innovation instruments, where you will be still funded around 70% of your costs. That generally requires you to join a consortium. So that's what Henrik was mentioning. What do you do if you don't have such a consortium? Well, there are networking tools, communities that you can join. I'm happy to provide you with the details offline. You will see also on each calls specific requests for collaborations that you can also tag on the website of the Commission. But these are normally not very effective. The best way is really to go to a specialized community where you know that some of the players will be responding to those calls, or to companies who help assembling this consortium. There's a multitude of them helping with preparing the consortium and preparing the application. It takes a lot of time, so this is something you should really plan in advance. If you spot a topic that is interesting for you in a work program, these are published every 2 years. If you spot the topic that is interesting, you should immediately go and look for a consortium at least 6 months in advance, if not more. Because if you come, 2 months before the deadline, all the consortium are already assembled. They probably are finalizing their presentation proposals, and you will not have any chance. This is a competitive process. Only the top 10, 15% of the applications are funded, sometimes even less. And so you need to be working on this for at least 6 months, not 6 months full time, and you don't have to do all the work. When you're part of a consortium, you will be providing some elements of the proposal, and generally the coordinator, in the case of Equality, Capgemini, or the specialized consultancy, in the case of Equality, it was Vinci Labs, will be helping creating this full application, and they will be taking the text from the different partners. It can be small consortiums, 6 to 8 partners, or it could be very large one, up to 30, 40 partners, depending on the type of calls. There are even specific instruments that we already touched on US Seeds, which are mono-beneficiary, where you can apply on your own in the EIC program, called the EIC Transition or EIC Accelerator. That's a separate, of course, way of accessing the funding. So do not hesitate. It's really a good way to get into collaborations with large players. For us, for example, Vinci Labs, we're a quite small company, but this project Equality gave us a chance to interact with great companies, large companies like Capgemini, like Airbus, or even Pascal in quantum. So that was very, very good for us, very interesting to be able to talk to these companies and work with them. All right. There are 3 questions, or 4 actually, we could not answer in the time being, but I think we ran out of time. So I would like to thank everyone for contributing, all the speakers and the organizing team that made this possible. This is recorded, so you'll be able to get access to it, of course. If you need to reach any of the panelists and speakers today, please feel free to email us, and we'll for sure make the connections with the right people. Thanks again for joining today, and have a good day.